We're obviously going to be encountering a lot of equations during this course, so we need to have a very clear idea of what an equation is and what an equation isn't. So fundamentally, we can describe an equation as a statement about the equality of two expressions. What I'd like you to do to start with is have a look down this list and see which of these you agree with, which of these statements is true and which is false. Pause, make your decisions, and then continue. Okay, our first one, this is an equation. 1 add 2 equals 4 minus 1 counts as a valid equation. Remember, an equation is a statement about the equality of two expressions. This particular statement happens to be true. 3 equals 3. The second, 1 add 2 equals 4 plus 1, is also an equation. This particular equation is not true, but that doesn't stop it being an equation. It's a statement about the equality of two expressions, and this particular one happens to be a false statement. The next one is also an equation. You might look at it and think that's just a mistake, because if you were expanding x add 1 in a bracket squared, you wouldn't get x squared add 1, you get x squared add 2x add 1. But all that means is it's not necessarily true for all values of x. That doesn't necessarily mean that there are no values of x for which it is true. And even if that were the case, the definition for an equation is that it is a statement about the equality of the expressions. There may be values of x that make this true, and solving the equation is what you would be doing in order to find those. 5x squared minus 3x plus 1. Not an equation, because it's just an expression. You might look at a quadratic and immediately think I'd like to solve that quadratic equation, but if it doesn't have an equal sign, it's not an equation. It's not asking you to identify a particular value of x that makes it true, because it's not making a truth claim at all. It's just giving you a calculation that you could apply. The next one, this is also an equation. There are two expressions and they're equal to each other. But you might recognize it as an equation that has no solutions, because there are no values of x that you could add 3 to, which will give you the same result as if you added 4 to them. You can see it by trying to solve. As soon as you subtract x from both sides, you get 3 equals 4, which is just as false as the second equation we saw. X add y equals 4. This involves multiple variables, but it's still an equation. It's still a statement about the equality of two expressions. And in this case, there are values of x and y that would make it false, but there are also an unlimited number of values of x and y that would make it true. As long as you pair them up properly, they work. The solutions to this would form solution pairs. So there would be a value for x that goes with a value for y. And just because x could be 3 and y could be 7, they couldn't simultaneously be 3 and 7. So your solution would have to be 3, 1, where x is 3, y is 1, or potentially minus 3, 7, where x is minus 3 and y is 7. The next one down, this one might look like all that's happened is we've simplified an expression or expanded a bracket. It is technically an equation, but you might notice that it's an equation where the statement is true for all values of x. The last one, this breaks the rule because although it is comparing two expressions, it's not talking directly about their equality, it's an inequality. There's a subtle distinction, and many of the tools that we use for equations we also employ when we're dealing with inequalities, but it is different. When we solve an equation, we're finding a set of valid solutions, and that might be a finite set, it might have nothing in it, there might be no values that solve it, it might be an infinite set of values. But an inequality is by its nature going to have, if it has solutions, it's going to have a range of possible solutions. So in general, we think of the values that make an equation true as being the roots or the solutions. If an equation is always true, in other words, the equation or the statement holds true for any value of x or for any value of whatever the variable is, we call it an identity. This one is a good example of an identity, because the left-hand side and the right-hand sides are always the same. And this one is a more useful example of an identity because it's one that you will make use of every time you expand brackets or factorize things. You're making use of an identity. You're saying, I don't know what x is at this point in the problem, but it doesn't matter because whatever x is, this expression, x times x add 4, is definitely going to be equal to this other expression, x squared add 4x. You can also have the opposite, an equation which is never true, and we call it a contradiction. That would just be an equation that has no solutions. There are no values of x that make it true. 1 add 2 is never equal to 4 add 1. X add 3 is never equal to x add 4. Generally speaking, it can be helpful to think of an equation graphically. If you're trying to visualize what it means for an equation to have multiple solutions or no solutions or an infinite number of solutions, well, we can think of the equations of the graphs that correspond to the left-hand side and the right-hand side of your equation. So if you want to make sense of x add 3 equals x add 4, we could draw the graphs of y equals x add 3 and y equals x add 4, and they look like this. We start to realize, yes, there are lots of values of x that give you a corresponding value for y. When x is 3, y will be 6 if y is equal to x add 3, but we cannot simultaneously get the same value of y for any given input for x. No matter what x is, the value that y will take necessarily has to be different for each of those two equations. One way to say it is that the lines never cross. They're parallel lines. There are no points on the entire two-dimensional plane where you are on both lines, if you like. And as you can tell, if you draw a couple of random lines, there will usually be a single point where they cross. If you make up two random straight line equations, there will generally be a single point where both straight line equations are true. That will be the point where the two lines cross. But if your two lines happen to be parallel, then they never cross. You have come across simultaneous equations before. You'll have worked on these during your GCSE. I'd like you to try these three different questions and pay close attention to the method that you use to solve them and think about the results that you get. They're not designed to look particularly tricky, but they behave in some slightly strange ways. So pause the video, have a go, see what you come up with, and then unpause and we'll see what we find. So you should have, for the first one, x equals 4 and y equals 0. There are many ways you could solve this one. You might rearrange the first equation. So instead of writing this as x add y equals 4, maybe you write it as x equals 4 minus y. And then wherever you see x in the other equation, you could replace it with 4 minus y. And you could rearrange and solve and find y. Probably the simplest method is to use elimination. If we take the left-hand side of the second equation, and then we subtract from it the left-hand side of the first equation, we'll get just x, because y minus y disappears. We're allowed to do the same thing to both sides of an equation, but we use a bit of sleight of hand here. What we subtract from the right-hand side needs to be equal to what we subtracted from the left-hand side, but it doesn't need to be written in the same way. We subtracted x add y from the left-hand side. We're going to subtract 4 from the right-hand side, because the first equation tells us that 4 is equal to x add y. And when we do that, we have 4 on the right-hand side, we had x on the left-hand side, so now we know x is 4. You can then go back to either of the equations, or preferably both, so you can test your answers and see what y would be when x is 4. And we find that y happens to be 0. The next one has no solutions. I don't know if you got stuck trying this. Maybe you attempted a similar process to what I've done on the first example, where you subtract the left-hand sides, you subtract the right-hand sides. If you had, you'd have ended up with a contradiction, 0 equals 4, or something like that. If you tried substitution, you get the same problem. What this means is there are no values of x and y that simultaneously add to make 4 and also add to make 8, which makes sense. If they add to make 4, they can't also add to make 8 unless 4 and 8 are the same thing. And the last example is in some sense the opposite of this one. There are an infinite number of solutions. And the reason for this is that the second equation is just a scaled up version of the first equation. It may look slightly different, and sometimes an equation can be moved and manipulated around so it looks very different to a different equation, but under the hood they might be exactly the same algebraic creature. Graphically, this is what they look like. If you've got a pair of straight line equations that represent different lines and those lines are not parallel, then they will cross somewhere. And what we're doing by finding the values of x and y that satisfy the equations is identifying the point where the two lines cross. If they have no solutions because the two lines are parallel, then the straight lines are never going to cross because they're going in the same direction. And then the infinite solutions alternative, it's a little hard to see on a graph because the two lines are the same line. Another word for that is coincident. The two lines are coincident. It's based on the same root as the word coincidence. It's a line which occurs at exactly the same places as the other line. So any point which is on the first line is also on the second line. If you can find a pair of values x and y that add to make 4, then if you add 2 lots of x and 2 lots of y, you will get 8. Just be a little careful here. Simply saying there is an infinite number of solutions does not mean that anything is a solution. X and y cannot be just anything, but provided you found a point which is on the first line, and there are an infinite number of points on the first line, then it is also a point on the second. Let's try an example now from the book. This is from exercise 3A, question 4. Because at A level, we typically have a little more complexity built into the problems. In this case, we have 3x add ky equals 8 and x minus 2ky equals 5. And the question is asking us to find the value of x, even though they haven't told us k. And then in part B, they tell us the value for y and ask us to calculate the value of k. So there's 3 different unknowns going on really in this. But in general, we can still apply the same techniques we've used before. If you're solving linear simultaneous equations, you can use elimination or substitution. Elimination is where we do something clever with the left-hand side and the right-hand side, like we did in the previous example. Substitution is where you would rearrange to make x or y the subject of one of your equations, and then substitute the result into the other one. In this case, I'm going to use elimination. I've noticed that if I double the first equation, I can eliminate the term involving y. Not only that, but I'll be able to eliminate k as well. So this was a useful idea. I'll get 3x turning into 6x, and I'll get ky turning into 2ky, and then 8 turns into 16. And the useful bit here is that 2ky positive in this equation will link up nicely with the minus 2ky in the second equation. So I'm going to add the two equations. I've put the word adding in inverted commas because, of course, we don't add equations. They're statements about the truth of something. So they can't be added together. They're not numbers. But it's a convenient shorthand way of saying what we mean. We're going to add the left-hand sides together. And what we should get is something equal to the sum of the right-hand sides, because the left-hand side of each is equal to the right-hand side of the same equation. So we can combine them in this way, and we get another valid statement. Well, when we do that, the 2ky term and the minus 2ky term from the other equation disappear and cancel out. And we get 7x on the left-hand side. 16 add 5 gives us the 21 on the right-hand side, so x is 3. And that's exactly what they were asking us to show in the question. You might be a little surprised that even though we don't know k, we still are able to find a value for x. That's because of the connection between k and the rest of the variables. K only appears as a multiple of y, and that allows us to eliminate it at the same time as y. We get 2 for the price of 1. But now part B gives us an extra piece of information, because without knowing y or k, we wouldn't have enough information to calculate the other one. As a general rule of thumb, you need 2 pieces of information to find 2 unknown values, and you need 3 pieces of information to find 3 unknown values. If the information you've got is not helpful, like a second equation which is really just a scaled up version of the first one, then that may not be sufficient. But if you've got distinct and useful pieces of information, like we've got 2 equations and a fact about the value of y, that should be enough to determine the value of k. So when we use y equals a half, we can go back to, let's say, the very first equation and substitute them in. We know that x equals 3. We got that here, so we can put that in there. We also know that we've been given y equals a half, so that can go in here. And we're substituting it directly into the equation. We rearrange and we can find k. We get k equals minus 2. The last thing you should do, in general, you should do this every time you solve any sort of equation. Provided it's relatively quick to do, you should find a way of verifying your answer by checking. And in this case, with simultaneous equations, we used the first equation to find our value for k. So I'm going to use the second equation to test, to check that it works. So I'm putting x in here. I'm putting y in here. And I'm going to try putting my value for k in here. And then when we work all that out, it comes to a 5. And 5 is exactly the number we were hoping for, because according to the equation up here, we should get 5 on the right-hand side. Now, if you're curious about what these lines look like, this diagram might help you. And it also illustrates nicely why the value of x does not depend on the value of k. We didn't need to know what y was or what k was to answer part A of the question. These two lines do change, they both change, but because of the way the lines are structured, k could be anything, and the crossing point is still going to have an x coordinate of 3. You can also see, if you look closely, when k takes a value of -2, the crossing point seems to be at the point 3.5. Now you can have a go at a couple of questions from exercise 3a, questions 3 and 5. Now we crank it up a notch and we look at what happens when, instead of having two lines crossing, we have a line and a curve. Let's start with an example. We've got a straight line, y minus 2x equals 3, crossing a quadratic curve, y equals 2x squared minus 5x minus 1. We're told that it crosses in two places and we need to find the coordinates of both. Now, because we're looking for coordinates, that'll be an x value and a y value, but because there are two different points where the line crosses the curve, we need the x and the y value for each point. There are 4 numbers we'll be looking for, and it matters which one is labeled x and y, of course, and it matters which x and y value go together. Because if you've got the point 2, 7 and the point 3, 4, that's different to the point 3, 7 and the point 2, 4. Generally speaking, when we're dealing with simultaneous equations that are more complicated than just a pair of linear equations, we tend to fall back on substitution. There are some situations where you can still use elimination in some form or another, but in general, if you've got a simple equation, it'll be quick enough to rearrange it to write x in terms of y or to write y in terms of x, and then you can take that new expression, substitute it into the bigger, more complicated equation, and your complicated equation will become something which still might take a bit of work to solve. In this case, it looks like we'll have a quadratic equation to solve, but it'll just have one variable in it, either x and x squared and numbers, or y and y squared and numbers. So I'm going to talk you through the steps, and then I'd like you to pause the video and try to follow them. The first thing you'll do is try to write y in terms of x to make y the subject for the linear equation, the blue one. And then substitute that into the quadratic equation, which I've circled in green. That should allow you to eliminate y from the quadratic equation. You'll have something that only involves x. Next, you simplify, you rearrange. There'll be a quadratic equation in x, which means you should be able to solve it. You can do that in a number of different ways, including using your Casio ClassWiz calculator. And step 4, use the linear equation then to go back and generate the corresponding y value for each of your x values that you found. Give it a go, and when you're ready, continue the video. So in the first step, we just have a little bit of rearrangement to do, add 2x to both sides, and we now know that y is equal to 2x add 3. In the quadratic equation, it's also relatively nice here because y only appears in one place. We can just replace it directly with 2x add 3. And it doesn't take very much work to rearrange now. We subtract 2x from each side and we subtract 3 from each side. I've written it the other way around as well. So we have 2x squared minus 7x minus 4 equals 0. Now you can solve this, as I said, in a few different ways. Generally speaking, unless you can quickly and easily factorize it, then it'll be better to pick up your calculator and plug the numbers in. The calculator will do the hard work of substituting into the quadratic formula for you if you use the quadratics mode, and then you can jump straight to the solutions. But if you did factorize it, this is what you would have got. Once we have those solutions, x equals 4 and x equals minus a half, we can then move on to step 4, where we substitute each of those into the linear equation once more. So y equals 2 times x add 3. So we try y equals 2 times 4 add 3. And now we know that the y coordinate that corresponds to an x coordinate of 4 must be 11. And similarly for the next one. So we've got our 2 points. You should be able to try this exercise question now. But just before you move on to that, have a quick look at this graph. I want to talk briefly about what the weird red graph is that I've included. The two black graphs are the curve and the line that we were interested in finding crossing points for. And you can see the coordinates if you look closely. 4, 11 is the first one we found, and -1/2, 2 is the second one. Now, the red curve is also a quadratic. The red curve gives us the difference between the straight line equation 2x add 3 and the quadratic equation 2x squared minus 5x minus 1. Essentially, what we're looking at with that red curve is the equation y equals 2x squared minus 7x minus 4, because that is a related equation to this simultaneous equations problem. We started with two different curves, if you like. One of them was a straight line, but effectively we've got two different functions. We want to know where they cross. But when we combine them and simplify and turn it into one expression equals 0, it's now equivalent to saying, where does y equals 2x squared minus 7x minus 4 cross the x-axis, the line y equals 0? And you can see, if you look closely, the red points where the red quadratic crosses the x-axis correspond perfectly to the x-coordinates of the crossing points between the quadratic and the line that we had at the very beginning. Now you can try 3b, question 4. And when you're done with that, come back and we'll look at some more examples. Now let's try a trickier one. We still have a straight line equation here, 2x add y equals 4. But the curve has equation 9x squared add 4y squared equals 36. That's not the sort of equation you're used to seeing or sketching, I would imagine. Not at this point, certainly. It's still, in some sense, quadratic, but it's not quadratic in the simplistic sense that we've previously thought of it. Y equals something x squared plus something x plus something. This one's a quadratic that involves x and y. And there's all sorts of different kinds of curves you can generate from things like this. The circle equation is a classic. X squared add y squared equals a radius squared is in some sense a quadratic equation, but it's a quadratic involving x and y. And therefore it doesn't give you the standard parabolic graph, it gives you something else. In this case, this one's not going to give you a circle, but it will be similar to a circle because it's a little bit like x squared add y squared equals something. And you'll be reassured to hear exactly the same method we used before will work just fine in this case. We're going to apply substitution. We take the simpler equation, we find a way of making either x or y the subject, and we substitute it into the more complicated one. There's more work, but not a huge amount more. So we can write y in terms of x again, we can substitute, we can simplify, rearrange, and then use the linear equation to find the y value. Pause and have a go at this question for yourself and see how different it feels to the previous one. Once you've found your solutions, continue the video and we'll see if we agree. So we should have y equals 4 minus 2x. Then we can substitute 4 minus 2x in place of y. Be careful here because you need to square the entire bracket. And once you've squared it, you've got to multiply it by 4. So we've got a bit of working out to do here. We'll get this beastie, which can be simplified to this epic looking quadratic. And then we'll get solutions x equals 2 and x equals 14 over 25. And each of those solutions corresponds to a y value, which we can get just by looking back at what we had in step 1, y equals 4 minus 2x. That's the simplest way to get the correct corresponding y value. Once you've got those, we can look at the graphical representation of this particular problem. The shape happens to be an ellipse. You can start with a circle equation like x squared add y squared equals 36. That would be a circle with a radius of 36. With a radius of 6. And then you could start distorting it and stretching and squashing in different ways. And that's what's happened here. So there's been a distortion so that in the x direction, it's been squashed by scale factor 3, or a stretch of scale factor 1/3 horizontally, if you like. And in the y direction, it's been stretched by scale factor 1/2. So it's been squashed in the y direction, but not quite as much as in the x direction. So it ends up looking like some kind of vaguely egg-shaped thing. We can see the crossing points between the line and the curve, and they correspond nicely to what we had down there for our coordinates, 2, 0, and 14 over 25, 72 over 25. Just a quick note, although you can write these as decimals, the general principle in maths is to leave your answers as fractions in their simplest form, even if they end up being top-heavy fractions. It's okay to write these ones as decimals because they do actually turn into relatively nice terminating decimals. You don't have to round anything. You definitely shouldn't round things. If you're giving an answer, unless you're told to give an approximate answer, you should give the exact answer. But although decimals are generally fine as long as they're exact, you should steer clear of mixed numbers. We don't want to be seeing 2 and a third when you could otherwise be writing 7 over 3. Now there's a few more questions you can try from 3B and 3C, so give those a go and then tune back in for the next bit. The last thing I'd like you to look at on this page before we move on is this characteristic quadratic. In other words, it's a quadratic that tells us something about the original scenario. We have an ellipse crossing a straight line, but somehow all of that got reduced to a quadratic equation that we needed to solve and find solutions for. What would happen if we get to that point, we have a quadratic equation, and it has no solutions? And what would happen if we got to that point and we found that the solutions were the same? It had a repeated root, just x equals 3 and x equals 3. Have a think about what that means and what that would mean for the line crossing the ellipse scenario. The next thing we're going to look at is a little beyond the simultaneous equations themselves, a bit more generalized. We need to think in terms of how the discriminant of a quadratic can inform us about the results of solving simultaneous equations without necessarily needing to solve them. So you'll be able to find this snippet from your book. This is quite useful because it will remind you, first of all, about the discriminant. If we're trying to solve a quadratic equation, ax squared add bx add c equals 0, then we have 3 possibilities. And we can discriminate between the 3 possibilities using that term from inside the quadratic formula, b squared minus 4ac, the stuff that usually lives inside a square root sign. Because if it's positive, then there'll be 2 different square roots, and you'll have the positive square root and the negative square root, and you'll be able to find 2 different solutions. If it's 0, then you'll have negative b plus or minus 0 all over 2a. Which means your 2 solutions will end up being the same. Adding 0 and subtracting 0 makes no difference. If it's negative, you can't square root it using just real numbers. So that means there are no real solutions. There are no numbers that can work in there if we're stuck within the realm of the real numbers, which you are throughout A-level maths. So we can move beyond now the idea of just a quadratic equation representing a quadratic graph that either crosses or doesn't cross the x-axis, because if you have simultaneous equations that you are solving and the resulting equation that you create is a quadratic, the nature of the roots of that quadratic correspond directly to the nature of the crossing points of your simultaneous equations. Look at the examples in these pictures. The lines are not necessarily horizontal lines like the x-axis, and we can get even more general than this because the curves don't even need to be parabolas like they are in this diagram. They could be circles or ellipses or hyperbolas like a y equals 1 over x graph. And this property will still work. If the quadratic equation you generate has no solutions, that tells you the simultaneous equations don't cross. The 2 curves that you're trying to solve simultaneously have no intersection points, like the situation on the right. If, on the other hand, you get 2 solutions, then yes, it crosses twice. Goes into the circle and then out again the other side, perhaps. If you get a repeated root, that's the more interesting one, because it means the circle and the line, or the parabola and the line, cross at just one point. In other words, they just touch. We use the word tangent. Just like for tangible, something is tangible if you can touch it. A tangent line touches a curve just at a single point. So it doesn't miss it completely, it doesn't go in and then out, it just brushes the surface. So we could use that to solve problems like this. Show that x add y equals 2 doesn't cross the circle x squared add y squared equals 1. Well, you could draw this out as a little diagram on a set of axes for yourselves if you like before you begin, and you'll see that as it happens, the line does seem to go fairly close to the circle. It's not immediately obvious that it wouldn't cross. But when we do the calculation, we find, firstly, we can substitute in for y. Y is equal to 2 minus x. And when we replace y with 2 minus x and simplify, we get something like this. We can expand out that bracket, square the entire thing. You get 2 minus 2x minus another 2x and then plus x squared. When we include the other x squared that was already there and we subtract 1 from both sides to get our quadratic in the standard form for solving, this is what we end up with. 2x squared minus 4x plus 3 equals 0. Then we can test it with the discriminant. I'm not trying to solve it, I'm just picking out the discriminant and seeing what that tells me. And look at that, the discriminant is negative. So our final conclusion is, well, when we looked at the discriminant, we got a negative number. That means there are no solutions to my quadratic, but my quadratic was going to give me the x-coordinates of the points of intersection of my original curves, so those original functions do not cross. The line never crosses the circle. Bonus question for you. For what values of k would the line x add y equals k be tangent to the circle x squared add y squared equals 1? So we tried x add y equals 2. Turns out it doesn't cross the circle. That line is too far away. Presumably there are values of k where the line does cross the circle, goes into it and then leaves it again. There might even be a value of k that you can think of where the line cuts through the middle of the circle. But can you find the boundary points, the values of k for which the line just touches the circle at a single point? Then you can have a go at the last 3 questions from exercise 3C.